Professor Ciarlet, and all the senior fellow, ladies and gentlemen. I'm Jacob Huang. I'm the Executive Director of IAS, so sort of your host. If something wrong, please just tell me. We can try our best to make you comfortable. And this afternoon, we're going to have another 3 talk, starting from Professor Salençon. And I hope we can probably finish on time. Therefore, we have some spare time to visit our museum. It's a very interesting one. So because the president has some special meeting, so we will postpone our dinner until 7 o'clock. So we'll leave CDU at 6:30, right in the AC3 building. So the museum will be on the 18th floor of the museum, that building, and we will stay there for about half an hour. So I think we do have time. Yeah. Oh, only for the conference speaker. Oh, okay, yeah. Okay, so I think we're going to be very exciting this afternoon. We had the first talk by Professor Salençon, and Professor Salençon is a very famous scholar. He's the also from France, the member of the French Academy of Science. As I remember, he was probably the chair of French Academy of Science. Wow, very important. And also he's the member of French Academy of Technology, member of American Academy and European. Yeah. And also he's a long-term ISD fellow. I think he was probably one of them who actually gave a lecture for the whole semester in mechanical engineering department. So he will probably do the same in future. And so today he's going to give a talk from Galileo, from metals to mechanics. So let's give a warm applause to Professor Salençon.
Thank you so much for this kind introduction. As all my colleagues, I will, of course, start with saying very happy birthday to Philippe. By the way, I must say that next year it will be 60 years since I first met Philippe Ciarlet. We were at the same school, Polytechnic school. And then we were supposed to be at the same school also, École Nationale des Ponts et Chaussées, but by the time, Philippe had already found a way of doing research, which was not my case, and so he was working in CEA as far as I remember. Well, so it's thanks to him and thanks to CTU, we got acquainted together more or less 8 or 10 years ago when he visited me with Professor Wakewood at the Academy of Sciences. I was chairing at the time. And since that time, we are getting closer and closer. As was said, I've been teaching here at CTU for 5 years, 3 years and 2 years. And I've been a senior fellow for the remaining years. That's 3 years from until now. I've been giving classes, and I hope to be able to give classes again. So now let us go to begin at the beginning. And we will follow Galileo from matter to machines. I must say that after we have heard this morning, what we have heard this morning, I could say we are going down to earth. I'm very ashamed and humble of what I will be telling you from now on. Well, I have to find this. Right, I'm not quite accustomed with this, but I think I will manage. So here is Galileo is his name, and I will speak about the discourses, the famous discourses which were published in 1638. Although Galileo started writing them in 1592, so it took a long time. And he finished them when he was not in jail, but in residence, what we should say, after his trial. I will refer to the English translation, which was by Henry Crewe and Alfonso de Salvio, which appeared in 1914. And in that translation, you find an introduction by Antonio Favaro, and where you find some appreciation by Galileo on his own work. this is superior to everything else of mine, either published. And then a treatise on a new branch of mechanics full of interesting and useful ideas. So I will try to show you some interesting and useful ideas. Well, but I remember Voltaire, who said, le secret d'ennuyer est celui de tout dire. I tried to translate it. The secret of boring is that of saying everything. So I will try not to bore you. So I could draw a conclusion, say nothing. By the way, I will try to say a few things, by the way, 2 topics. So here are the contents. 2 topics will be yield design of structures and dimensional analysis. And among those 2 topics, one is more equal than others, as Orwell used to write it. So let us start with Galileo's approach to the strength of matter. As you understand, the discourses are dialogues. They are translated in English by dialogues. Dialogues means the voice going to and fro. Dialogues between 3 people, Salviati, Sagredo, and Simplicio. And Salviati stands for what we should say now, the spokesperson for the academician being Galileo himself. So Salviati will give the answers supposed to be Galileo's answers. And in the first day and second day, there are 4 days in the dialogues. Now, first and second day are devoted to what we call now strength of materials. So we will see what Galileo's approach to strength of material is. It starts, as I was saying it are dialogues, it starts with a question. Is it possible to increase proportionally means geometrically, proportionally, the size of a machine? And after a question, you have the answer. And the answer is Salviati's answer: the larger the machine, the greater its weakness. Well, once you have the answer, you have a new question. My question is, why? Why? So, you may think of imperfections. Matter is imperfect, you have imperfections, and of course, if you enlarge the size of the machine, the odds are against you, and so it will be the reason why. But Galileo discards this reason. No imperfection. Even if matter were perfect, even in that case, still, the larger the machine, the greater its weakness. So where is the reason why? What is the reason why? The reason lies in resistance of matter. So he has to define what resistance is, and he defines it through a longitudinal pull test. So you have this specimen, and an active force, which is the weight. It is a figure 1 in the treatise. An active force is active, and he says that it is clear that if you increase the weight, then one day or another, the specimen will break, like a rope, he says. The solid will break. So this is the definition of the resistance of matter, and we have to keep this in mind. So it is defined through longitudinal pull test. Further on, Galileo remarks that this resistance will be proportional to the cross-section. So also this we keep in mind. But you must understand that in the dialogues, things are going to and fro. For instance, this is figure 1, this is figure 20. And between those figures, we have already a discussion about other things. Then, once we have resistance, why still we do not have the answer? Larger the machine, greater its weakness? Well, because there is some kind of a competition. There is a competition between active forces that are acting on the machine, and resistance of matter the machine is constituted from. And we have to know what this competition is. So we have to define the competition. The competition, I forgot my material, experimental material, is here in my pocket. Should be just always a problem. Not with the computer. this rule, that's all. I will not break it, by the way, anyway. So, in order to know what competition we have, it starts with a remark. Galileo remarks that if I take this prism, bar, you call it like as you like, maybe a ruler, it is very difficult for me to break it by pulling it that way, but it is quite easier to do it by bending it. So, why? And then we will see what the competition is. This is the famous problem of the cantilever beam, finely illustrated here, as you see. And in this cantilever beam, we have to know what the active force is on where the resistance is exerted, where the resistance lies. Well, the active force, obviously, is the weight of this bulk of matter here. Let us suppose that the beam is weightless. So this is the active force. But where is the resistance? Resistance, remember, is defined that way. It's a longitudinal pull test. So we don't see where we have longitudinal pull test here. Sometimes it works that way. So Galileo says, well, it is clear that if the cylinder breaks, fracture will occur at point B here, where the edge of the motors acts as a fulcrum for the lever BC. So here we have resistance. Where? But now how? For this, we must imagine what Galileo did. First, geometrical modeling. We forget about, well, this nice drawing. We just see the beam. Then, mechanical modeling. Mechanical modeling is a lever. And the word lever was already present in what we read before. Mechanical modeling is a lever, so we have active force acting at this point. This is the long arm of the lever. And we have resistance acting at this point. This is the short arm of the lever. And finally, we have the answer to the question over there. What competition is it? We have to write the equilibrium of that lever. So the competition is just the balance between active force and resistance. Active force refers to the structure. Resistance refers to material. So on the one side, structure, other side, material. And this is an interesting and useful idea. This is the basis of what was developed afterwards as the yield design theory. And so now we will go into the yield design theory. Yield design of structures. So we start from this an idea of a balance that should exist between active forces and resistance forces. And we must say that it has been, well, the root of stability analysis of arches, vaults, bridges, retaining walls, everything. Public works, for instance, during centuries and centuries. If for those who are interested, you can look at the works by Jacques Heyman. This reference gives you all the work, and this is, I think, the best way to know about all the stability analysis of arches. In fact, people were using two heuristic statements. The first statement says that if you can find an internal force distribution, internal forces are the forces in matter, inside the structure, internal force distribution, that is in equilibrium with the given active forces, and at the same time, I would say our president, at the same time respect the limits set by the resistance of matter, then the structure will be stable. That is what was the first statement they would use. A second one, if a collapse mechanism can be built up where the work, now we're speaking of work, where the work by the given active forces exceeds the work developed by resisting forces, then the structure will be unstable. And by the way, those two statements may look quite obvious. And in fact, we know that these heuristic statements are possibly misleading. Why are they possibly misleading? The first one, because obviously the condition that is written here is just a necessary condition. It is not a sufficient condition for stability, what they call stability. So it will only give you upper bounds for what we call safe loads. So from this viewpoint only, it is possibly misleading. As far as the second statement is concerned, it is a little bit tricky. The problem comes with the work developed by resisting forces. There is a problem in evaluating the work developed by resisting forces, and sometimes you will evaluate a work which is not right. And it results in the fact that those two statements may happen to be in contradiction with each other. So clearly there is a problem. So as I said that I didn't say that, but I will try not to bore you. I will make the long story short. And I will jump from Galileo, 1 century, jump to Coulomb. You already saw him, but he was tiny. This one is bigger. It is the same Coulomb as we saw this morning. And about the stability analysis of arches, vaults, bridges, retaining walls. He wrote about that in a famous essay which was published in 1773. It's interesting to read the title, The Rules of Maximis and Minimis. This, for mathematicians, will recall Leibniz's work, title of Leibniz's work. So I will not go on about Coulomb, just to point out two things. First of all, he clearly pointed out the difference of status between active forces and resistance forces. Resistance, I would say. Active forces are prescribed. Either, in our case now, presently, they are prescribed by rules, by codes, but they are given. They are data, you know them. Resisting forces, resistance, are only defined, only characterized by a limit to the magnitude. So it is different. On the one side, you will have equations, on the other side, inequations. And what you have to write is the compatibility between those equations on the left-hand side and inequations on the right-hand side. Second point I will take from Coulomb's work is that he remarked also that exhaustive checking of compatibility between active forces and resistance is usually impossible. So if you cannot perform it. And what we can perform will be to check weaker necessary conditions, weaker necessary neither compatibility conditions, such as global equilibrium, for instance. And so this explains why, as I said, we had upper bounds. This explains why you will have to minimize. Well, this is, as mathematicians, you minimize. Sometimes also he wants to maximize, because Coulomb, for instance, was working on retaining walls, and of course he was looking either for active thrust or passive thrust. So he has to minimize or maximize. So those are the 2 points I am just taking out from Coulomb. Minimizing. So now we shall get in the theory of field design as it was developed during the 20th century. By the way, I should say that, in my opinion, it really started with the work by William Prager, which was about in the 1950s, and then it was followed by other people, mainly during up to the end of the 20th century. So it is, as it stands, I will show it as it stands now. We write the mathematical compatibility between resistance of materials and the equilibrium of the system. Clearly, this is the same basic assumption at the beginning. We have to check this. We check it, and we use two simple mathematical tools. So the first one is convexity, and the second one is duality. And then, from this, we reach what we call potentially safe loads. Potentially is just here, and should be here, to remind us that what we are doing is working on necessary conditions for stability. So, this is the way I presented the theory, well, this is 5 years ago here in CTU to students, PhD students. That we remark that loads and resistances play symmetric roles in the yield design rationale. So on this side we have loads. We will define them through loading parameters, which are scalar parameters. I will call them Q1, Q2, Qn. They will appear afterwards. And on the other side we have resistance parameters. Resistance parameters will be defined by known by R1, R2, Rm. So here they are. Here are those parameters. Difference is that here they are real. This one should be positive. Some of them could be zero, but not all of them. Otherwise, you don't have any structure at all. So maybe sometimes you may have one of them, which is zero. So you have the resistance parameters on the one side, loading parameters on the other. Then let us think. Suppose resistance parameters are given. So you know matter is given. And what you are working on are the loads. The loads can be changed. So what we prove is that assuming that the strength criterion of matter is convex, potentially safe loads generate a convex. Remember what potentially safe loads are? They are the loads for which compatibility between loads and resistance is satisfied. And also, it is, okay. So we define a convex. This convex, of course, is a function of the resistance parameters. So here it is. Since it is a convex, then you will be able to determine some potentially safe loads. And from convexity, you will derive that the convex Earl, you know what the convex Earl is, if you don't know it will appear, of potentially safe loads is an internal estimate of the domain which is here, the domain of potentially safe loads. Here is the convex Earl, and it is an internal estimate of this domain which we do not know up to now, which I want to determine. Here it is. So this reminds you of the first heuristic statement. But this one is mathematically strong, sound. But when you have an internal estimate, you would be very happy to have an external estimate. And this is possible thanks to duality. And duality makes it possible, as I say, to obtain an external estimate. And that is, external will be outside K. So outside K are certainly unsafe loads. Inside is potentially safe, but outside is certainly unsafe. So this way, you will get a dual definition of certainly unsafe loads. And for this, you will use virtual collapse mechanisms. Remember, we had collapse mechanisms in the heuristic statement. In this case, the important word is virtual. Virtual meaning that they don't have to comply with geometrical constraints, and also that maybe there will not be actual mechanisms. And so you will get this dual definition of certainly unsafe loads. All these in dark gray are certainly unsafe loads. And how do we get it? We get them by writing that the work by external forces is superior or equal to maximum resisting work. This is a difference with what we have seen in the second heuristic statement. Here, the maximum resisting work is mathematically defined from the knowledge of the strength criterion of matter, which was not the case in the heuristic statement. So from this point of view, there is no difficulty. You can read in the book. In front of the criterion, you have the maximum resisting work. It is just the dual function of the convex. And from this, with this, we have two consistent mathematical statements instead of the two heuristic statements we had before. But they are coincident with each other, but these ones are the good ones. They are consistent. So now let us look on the other side. You were looking, given the resistance, and we were looking at the loads. Now let us assume we know the loads, and we try to know what resistance is necessary for the loads to be potentially safe. Well, so we define potentially safe dimensioning for a given load, and they are defined through the fact that the load should be potentially safe with the dimensioning. Okay, so it is simple to understand. And it turns out that also they generate a convex. A convex in this cone, positive cone here. That is for instance, once you have one of these potentially safe dimensioning, obviously all this positive cone here is potentially safe. Obviously, because all the resisting parameters are greater than the other one, so the structure will be safe, sure. Then, from convexity, if you have many, you have this. And from convexity, you will say that the convex hull of those cones will be an internal estimate of the convex of potentially safe dimensioning. So here it is. And this is the one we are looking for. So it is the same, it is the reverse of what we had with when the loads, where the resistance were given. Now it is the loads that are given. And obviously we will get an external estimate through duality. We make it short now. It is that way. And it is obviously through virtual collapse mechanisms again. So now we have the other side, the other way of seeing it, looking at it. This is not so, it seems, well, more or less trivial maybe, especially for mathematicians. But it has some kind of interest, practical interest. And especially when you perform yield design dimensioning, sometimes you want to make optimum design. So optimum design for given loads will refer to this. And for instance, if the objective function is linear, but it is not always linear, it may be convex or maybe slightly concave or so. Then, for instance, if you have an objective function which is linear, what you will do will be to look for the minimum value of the objective function. But you can do it if it is a convex one or slightly concave, of course. So this is one way to look at optimum yield design dimensioning. Well, I am anticipating about what the practical applications. I must say that this has been used, for instance, by one of our colleagues, fortunately passed away many years ago, Antoni Savchuk, from Poland. And when dimensioning reinforced concrete slabs. This is what he used for that. So now we are looking larger and larger, and we will define the domain of potential stability, considering at the same time loads and resistance. Why did we separate loads and resistance? We can consider them together. So we consider them together, and we define in Rn cross R plus M, we'll define a domain. We call it K, capital K, wonderful K as you like it, and which is obviously the fact that you have this load vector, this resistance vector, and in fact it means that the load is potentially safe with the resistance, or the resistance belongs to the potentially safe dimensionings for the loads. Well, as you may imagine, convexity is still there. But in that case, what we find is that this domain is a convex cone with summit O in this space, I will call it. It is not actually space, but a convex. So that's why I'm not very good at drawings with many and many dimensions, so I try to show you what it looked like. Obviously, if you make some kind of a cut that way, if you cut it that way, for a given value of R, you get K. If you cut it the other way, you will get D. That's the same. Not necessary to see that. And for this, what is the interest of this one? It is probabilistic yield design dimensioning. And this is something we looked at carefully at the time, when it was a bit fashionable to use probabilistic design. And I think now people don't speak so much about probabilistic design. So imagine that you have a measure. This is a measure. A measure for both loads, probability measure, for both loads and resistance. You can have one for loads, one for resistance, and you multiply one by the other, and or not. So the probability of potential stability of the system is just the measure, is the probability of this Q and R to belong to K, and it is just the measure of K. So this is a simple, clear definition of probabilistic yield design. And this, unfortunately, has been overlooked. Then, we are not, actually, I would say that when people are designing structures, they are not so interested in probability of potential stability, but in probability of collapse. And so probability of collapse is 1 minus PS, 1 minus probability, 1 minus mu of K. And usually what people do in that case, if they are working with K, sometimes they were working separately, either given Q or given R, but they would not do both. They would use virtual collapse mechanisms. The problem is that in that case, you only reach lower estimates for the probability of collapse of the system. It means that if you don't use enough virtual collapse mechanism, you may dramatically underestimate the probability of collapse. Sometimes people were only using one family of collapse mechanisms because they say, well, this is the one that will most probably occur. And they were overlooking 1/2 of the probability of collapse, for instance. So this is one point, that is this mark here, that is one point that we have to be aware of. Second point is that obviously when people are designing such a kind of structure, they are looking at very low level of probability of collapse. They don't want to have 50% as a probability of collapse. So in that case, people working in probability will tell you, oh, beware of the tail behavior of probability laws, because the result you are looking for is highly dependent on the tail behavior of the probability laws you are assuming at the beginning. So you have to, those laws of those extreme value probability laws are to be discussed and carefully looked at. So that is what I wanted to say about the theory. So now the question is, what is the practical relevance of this theory? Well, those who are working in mechanics here, even people also working in mathematics, say, well, oh, this is wonderful, but you are speaking about potential stability, but we know now we have a lot of good methods to make step-by-step analysis with an elastic, elastoplastic, or viscoelastic framework. But what is important? And in that case, you must know initial internal force distribution, because a step-by-step analysis must start from something you know. You must know the loading history. You must know the full constitutive law of the materials. So if you know this, then you can perform this analysis, and of course we'll have a very, very reliable result. This is the basis, as far as the design of structure is concerned, of serviceability limit state design, that way. But the problem is sometimes, or often, as you like, depends on your view of things, is that in fact you are working with complete data. Incomplete data, most often about initial internal force distribution, about loading history, about the constitutive law. And in that case, all this will become, I would say, the significant will decrease, will become irrelevant. So you have to cross this. And what remains, which does not depend on all this data, what remains is yield design. So the yield design theory is still present in that case, and we will use it, for, especially in that cases. For instance, unfortunately, when you have to work with post-collapse analysis, post-collapse analysis, you don't know what happened, because if you knew what happened, you would have anticipated, and you would have designed the structure for this. So clearly, something happened that you didn't anticipate. So in that case, people do perform post-collapse analysis, and through the yield design theory. And in fact, they will find the resistance or where the problem was through the theory here. And this is the basis of the sound theoretical basis of what is usually called as ultimate limit state design. And it is a sound theoretical basis, I would say, that it gives, in the Eurocode, for instance, you have the load and resistance partial factors. You have a partial factor for modulus entity, and people sometimes have problems in defining them, and there is no problem once you are referring to the yield design theory. You see where you should put the factors, and especially when you have loads that are, how would I say, that are favorable or unfavorable. You may have the same load. For instance, it is gravity. Gravity may be unfavorable to the equilibrium on the one side, but it may be favorable on the other side. And in such a case, you should have two different partial factors, which is not quite really understood. It's clear. It clearly appears here. So that is the practical application, practical relevance. I would say also on this problem say a word about probabilistic dimensioning, which is not specific to yield design probabilistic dimensioning, but to probabilistic dimensioning by itself. And for this, I will quote a colleague. So it's a caveat. It's a caveat, and I will quote Nicolas Boulot. Any attempt to allow specific numerical value to the probability of a rare event is suspect unless the physical laws governing the corresponding phenomenon are explicitly and exhaustively known. This should or can remind you of what Pierre said this morning. You cannot think that because you are inserting probability laws, you are solving problems which you cannot solve otherwise. No, no. If you don't know, you don't know. Putting probability on it will not change the taste of it. Then, last topic, as I said, the first one was more equal than this one. Dimensional analysis. Well, we are still with the question. We have not answered the question why. We said, well, it's a balance, so not a why. The reason is that active forces acting on the structure of the machine and resistance do not follow the same scaling rules. So here I'm quoting Galileo. I'm certain, that's what Salviati is answering. I'm certain you both the other one, Sagredo Simplicio. I'm certain you both know that nature cannot produce a horse as large as 20 ordinary horses. So let us try to produce a horse as large as 20 ordinary horses. So this is a regular horse, the volume of the horse. So we're looking for the active forces on the horse. This is supposed to be the average weight per, this is average weight per unit volume, here it is, here. And this is the weight of the horse, is W. Then it should be inferior to resistance. Well, resistance, I will look here. And here, let's say that S will be the area of the bones, of the four bones, here, the legs of the horse. So if sigma 0 is the resistance of the bone material, then we should have this in equation. This will be satisfied. In other words, this ratio should be greater than 1. Now I will build a big horse. So this will be the big horse, lambda horse, I will call it. And so the volume of the big horse is V lambda. So section A will be S lambda. Resistance over gravity forces, here we are, obviously, resistance, gravity forces, this will be the resistance of the bones of the new horse. We don't know what it is. Volume, we know what it is, but this is lambda to the third, V. And this one, I leave it as it is. So, again, this ratio should be greater than 1. So let us assume that the horse, the bones of the horse, are made of the same material as the ordinary horse. This is what is written here. In such a case, in order to have this, we should have S lambda superior or equal to lambda to the third S, and not lambda square. So that is, well, Galileo saw it. Even the drawing here, enlarging the size of the bones, thus changing their shape until the form and appearance of the animals suggest a monstrosity. Well, so if you don't want to have a monstrosity, if you want to have a harmonious horse, then in such a case you have S lambda, lambda square S. And in such case, you should increase sigma 0 lambda. And then in that case, it should be lambda sigma 0, which already had been observed by Galileo on pouring material which is harder and stronger than usual. You know that, in fact, nature does both, enlarging and changing the material. Composition of bones is different, obviously. So what we see from this is that there is a dimensionless factor which governs the problem. Here is the dimensionless factor. And this is the basis of dimensional analysis, which is, by the way, the other interesting and useful idea I will deal with now. And this interesting and useful idea, if we look at the literature, we find Euler 150 years afterwards, more or less. Then French Joseph Bertrand, very good paper, very seldom quoted, very good paper, the compte rendu, and at the same time Le Rayleigh. And then in France, Vachy, because when we were young, maybe Philippe remembers that, when we were young we were told that the theorem was Vachy theorem, of course. One which is seldom quoted is Rabushinsky, and then well-known Buckingham. Although Buckingham quotes Rabushinsky, he acknowledges Rabushinsky as anterior to himself. But I think that worldwide the theorem is known as Buckingham theorem or pi theorem. And the usual wording says that any homogeneous relationship between quantities, etc., can be substituted by relationship between n minus p non-dimensional factors, pi I. So it comes from a common feeling, and to express the common feeling, I'm quoting Grisha, Grigory Barenblatt, group 1987. A common feeling says that physical laws do not depend on arbitrariness in the choice of basic units of measurement. Then we reach the notion of generalized homogeneity for functions, and this property allows the number of arguments in this function to be reduced, which is usually what people do with dimension analysis. I give you time to take the picture. It's done. Done. Yeah. So now we can try a more sophisticated approach, saying that the problem is set through a system of field differential equations, boundary conditions, and you have given values of quantities or fields for this, which are the data for the problem. And so the idea is that the problem, this system admits an invariance group, and the following idea is the solution to the problem should admit the same invariance group. Well, I put a mark there because there are some tricks. And this happens not to be true. They be the same, one may be wider or the other may be wider. It depends. So I will not go inside, or so 2 minutes left, so I will do it carefully. Well, I think that a full proof appeared in the 1960s, based upon the theory of arcwise connected subgroup of a vector group, a paper by Ayashida. And you will find this in a paper by Saint-Guilhem, which unfortunately is in French and unfortunately appeared in, I think, the Journal de Mécanique Appliquée or something like that. So unless I put it somewhere myself, nobody will find it. But here is the proof of this. Practical relevance. Well, it was already said by Grisha, dimensionless factor, then you get reduction of the number of arguments in the solution to the problem. But also, for people who are performing and designing, they have often to perform reduced scale experiments. And dimensional analysis provides similarity rules for reduced scale experiments. Last year, maybe the same day, it was a Wednesday, so you can calculate, but the very same week, my colleague Alain Péquer was making a distinguished lecture we had prepared together, and he showed this picture, which is a picture of the foundation of a big bridge in Greece. And this is at the width of is 90 meters. So it is actually impossible to make a test, obviously. You have to make reduced scale test. But the problem in soil mechanics, this is soil, is that you can't find a material, I would say, for the reduced scale test, which is homologous to the other one. You should use the same material. So you use the same material. So he said, well, we perform reduced scale test, and we have to centrifuge. So the question is, why a centrifuge? anytime I read this, I think of it's not Harpo. Yes, I think it's Harpo in one of Marx Brothers' movie where he say viaduct. Viaduct. He was speaking of a viaduct and he said viaduct. So I say wire centrifuge. That is a practical joke for me. Okay. So this is what they do. This is a regular soil. They were putting some kind of gravels, and you had this performance of the centrifuge. And so the explanation comes here. The scale is 1/μ. In order that the model be representative of the problem, initial problem, you should increase gravity, since it is the same soil. You should increase gravity, and gravity should be increased by the factor μ. So if this is 1/100, then gravity should be 100 times g. So this is the conclusion. Galileo's insight, as we've seen on these two examples, but not the only one, of course, the origin of theoretical research and practical applications actively referred to presently. With recent mathematical concepts, we could obtain complete proofs and statements for what were heuristic statements only. And also, it is an illustration of the inescapable nexus between materials and structures. So, here, Gosai.
Thank you. So now we open for Q&A section. Any questions from the audience? Okay,
Thank you, Jean, for this very interesting lecture. If I understood well, you could have a larger horse on the moon, for instance, because then the gravity is smaller.
Yeah, right, yes. We should try to build one, provided he can survive.
Yes, that's another question.
Yeah.
Just a comment.
Yeah.
Any other question?
What kind of materials could you use with improved properties? Because it depends on the resistance of the material.
Yeah.
So if you change the material, a new chemistry, a new type of composition.
In what case?
For the host, for instance.
Yes, for the host, I think nature does it. Because when you look at bones, it depends on the proportion of collagen on the one side and the word. I know the end of the word and I forget the beginning. Sorry, and I will be 78 tomorrow, so it's it's very bad for me. So, something appetite, something like that. The name is maybe like that. So the proportion depends. For instance, if you have a rat, the proportion much. It is collagen. Well, the tail of the rat is collagen. And when you need to have a very strong bone, you have appetite.
I think some people had looked at dinosaurs.
Yes.
So what?
Yes. When we were young, Philippe, we are now dinosaurs, of course, but when we were young, our professor in mechanics was Jean Mandel. I revert to Jean Mandel. But I think what he said was wrong. He said that the dinosaurs disappeared because of that. I think it is proved now that that was not true. That was not actually true. And by the way, in the printed text of this contribution, you will find a picture of the foot of some giant animals, for size, of course, giant animals, for fossils. I should say fossils, no, not fossils, fossils, they say. So, which I think this story about dinosaurs is not true now. But in fact, I believe that, of course, it was fully appetite. There was no collagen in the bones at the time.
Now my question was specific. How do you analyze the dinosaur? Because it's such a huge animal.
Yeah.
It has the same bones.
Yeah, yeah.
So
Yes, yes, you're right. Yes, so this is the reverse of the question. So our professor said they disappeared because of that, which was not true. And in fact, the way we analyze it is that the material was stronger, actually much stronger. So full of appetite and maybe something else. I don't know what kind of composition they found, because the bones, we can find them, so we can see what is left.
Okay. Any other question? Professor, from material science view, usually people say the strength is actually a function of defect or imperfections, but you say it is not.
Yeah, yes.
Comment. Mm-hmm.
Yes, well, I was just referring to Galileo's answer. You see, obviously, both viewpoints should be looked at. First of all, obviously, imperfection in matter makes it that if you enlarge the structures, the odds are against you. But this is not sufficient to explain. And so what he wanted to show was that there was a dimensional analysis, in fact. That is what he wanted to show.
Okay.
If you think of it, you will not find the same rules for probability of finding imperfections and the scaling rule. Okay. They will not follow the same rule. But obviously both are ready. But if it were, of course, resistance, by the way, is some kind of imperfection, of course.
Okay. We still have 2 minutes. Any question? I saw some new people from mechanical engineering department. No, I'm sure. Professor
no,
okay.
Usually we ask a question. I know you. I know you.
Thomas, yeah. You understand?
So I guess my question will be asking about that. So nowadays, the material science and chemistry building new materials every day. So is there a possibility that can actually build that monstrosity horse?
Yeah. Yes, what about the monstrosity horse? That is what you say. But in what sense?
In what sense is like there is material that actually can do such a structure that can actually make that happen? Because when you say same material, then it's impossible to do that. But what if I change the material?
Yes, of course. Yes. I'm not sure this monstrosity horse, which will not be monstrous if you change the material. He must live. You see, he must be a living horse. So I'm not sure with the material you are imagining it will be possible. But, well, if you go to civil engineering structures, for instance, obviously we improve material. John Lowe is not here, but you know what he did, what he managed to obtain as a material. So each time we reinforce material, we are improving in that way. One thing we should think of, actually, when we are improving materials, making composite material and so on, so it increases the difficulty of recycling. And people are forgetting about that. Recycling is there is some kind of antinomy between recycling and more sophisticated, complicated, reinforced materials. So, but you are quite right. You can make a horse, a lambda horse can make it.
Okay. Okay, thank you very much. Let's thank Professor Salençon again. Well, the second talk will be given by Professor Lin, and everybody know Professor Lin. He's members of French Academy of Science, foreign member of Chinese Academy of Science. I know he's also a foreign member of USA. Okay. And right now? Oh, okay. So we have 15 minutes break. Yeah, so let's have a coffee again.
Enjoy.